Geologists are journeying to the volcano known as Mauna Loa to investigate lava tubes, caves formed by molten lava of past eruptions, to test a suite of instruments for future missions to Mars. After arriving near the summit, the team set out on foot across the barren lava fields towards their field site.
So this is a lava tube, which is a subterranean kind of environment. And so it's analogous potentially to sites on Mars that we've identified from orbit.
Mars is also a planet with a lot of basalt and obvious volcanism in the past. And we can see with imaging from space that there's things kind of like this skylight behind me that might be an entrance to a subterranean cavern.
And so if life potentially exists there, that would be a great place to live because it's isolated from the surface, which is very hazardous for anything to live. Here, these tubes are actually teeming with life, and so they could potentially be relevant to what we might see on Mars.
While all four teams have the same destination, they're all here for different reasons. Let's meet the teams.
My name is Dina Bauer. I am a research scientist at the University of Maryland and NASA Goddard Space Flight Center. So our role is to look at the relationships between microbes and minerals, to understand better what signatures are left behind by the microbes and the minerals, because on other planets we're more likely to see minerals as opposed to actual living microbes.
I'm Heather Graham from NASA Goddard Space Flight Center. We're actually trying to look for life by the geology itself. We're looking for mineralogical complexity on surfaces. We're also looking at elemental abundances, just the patterns and distributions of elements on those surfaces. And we're trying to use those two pieces of data to build up an energy landscape. So by looking at those minerals and those elements, we can calculate how much energy would be available for certain kinds of metabolism that microbes in these caves might use.
Over long periods of time, microbial life leaves a chemical footprint in the rocks. While it's unlikely that modern Mars has living microbes today, future missions can seek out these footprints to determine if there once was Martian life.
Yeah, so this is a really classic spectrum that you would hope to see on another planet because these are pigment peaks. So you're not necessarily getting specific in terms of species, but you can at least say there's definitely a microbe here. So we're doing a suite of measurements, a combination of what a rover would be doing and return sample analysis. Very quickly, Raman spectroscopy is a vibrational spectroscopy technique. Basically, you're firing a laser at your target, and that excites the bonds. Each mineral has its own signature because when the light hits those bonds, they excite differently and produce a spectrum. And so I use that spectra that I collect to tell me what minerals are there as well as what organics are there. So when we find them together, it kind of helps us understand their relationships. If the microbes are actually part of the precipitation of those minerals, we can infer that from looking at the Raman data. And on the flip side, if the minerals were there first and we do see signatures of the microbes, we might say that maybe those microbes are taking advantage of the elements and the energy present in those minerals.
Oh, okay, look at that. Got me some cave water. Got me some cave juice. Hey, Dina, I found water. Yeah, I'm getting your drips. We take all of these data that we're doing with field instruments and we're mapping this in a co-registered landscape of the surface. So I hate to admit that I actually learned about this technique by watching an archaeology television show, but this is a common technique that people do in caves so that they can have